Every cubic centimeter of space around you is filled with ancient ghosts. They are the universe's oldest particles, streaming silently through your body right now, remnants of the very first second of existence. This is the cosmic neutrino background, a sea of nearly invisible messengers from the dawn of time. Think of it as the universe's ultimate fossil record, a snapshot frozen when everything was a seething, dense soup of pure energy. But we are only just learning how to read it. This faint background hum holds secrets to everything, from the violent birth of the cosmos in the Big Bang to the hidden nature of dark matter. By the end of this exploration, you will understand the 25 profound mysteries locked within this ghostly sea, puzzles that could redefine our place in the cosmos. What if this fossil record reveals that our universe is fundamentally different than we ever imagined? How does it feel to know you are constantly immersed in a relic older than atoms, older than light itself? This silence is the first great mystery. We know the sea of ancient neutrinos must be there, a fundamental prediction of our most successful cosmological model, yet we have never directly heard its whisper. The challenge is not one of rarity, but of subtlety. Billions of these cosmic ghosts pass through your thumb every second, but they are now so incredibly cold, so slow, that they have become almost perfectly camouflaged. Imagine trying to hear a single, specific cricket chirp in a stadium roaring with the noise of a million others. That is the scale of the problem. These primordial neutrinos, born in the furious heat of the Big Bang, have been stretched and cooled by the expanding universe for over 13 billion years. They now drift with so little energy that they are essentially frozen in place, their signals drowned out by a constant background hum from closer, more energetic sources like the sun, nuclear reactors, and even natural radioactivity in the rocks beneath our feet. Distinguishing the faint, cold fingerprint of the cosmic background from this relentless noise is arguably the hardest technical problem in all of particle physics. It is a needle in a universe-sized haystack where the needle itself is made of the same straw. So how do we even begin to look? The answer lies in experiments of breathtaking precision, like the proposed PTOLEMY project. Its goal is to capture these lethargic neutrinos using a target of ultra-pure tritium, a heavy form of hydrogen. The idea is that when a cosmic neutrino bumps into a tritium nucleus with just the right, minuscule amount of energy, it could trigger a specific, telltale reaction that nothing else can produce. Building such an experiment requires shielding it from cosmic rays deep underground, cooling detectors to temperatures near absolute zero, and eliminating every conceivable source of false signals. It is a monumental engineering feat aimed at achieving what would be a sure Nobel Prize discovery. A direct detection would be more than just a trophy. It would be a direct line to the infant universe. It would confirm, beyond any doubt, our picture of the Big Bang's first second. It would give us a pristine sample of the primordial particle soup, allowing us to measure its temperature and density with unprecedented accuracy. This first mystery, the quest to simply hear the oldest sound in the cosmos, is the essential key that unlocks all the others. That predicted temperature is a chilling 1.95 degrees above absolute zero. This number is not a guess, it is a precise mathematical echo. It is calculated backwards from the afterglow of the cosmic microwave background, the light released when the universe became transparent. The physics is beautifully simple in principle. As the universe expanded, it stretched the wavelengths of everything within it, cooling all primordial relics in lockstep. We know the temperature of the cosmic microwave background with exquisite accuracy, so we can calculate exactly how much colder the neutrino sea should be. This precise figure is a cornerstone of our standard model of cosmology. But here lies the second great mystery. We have never placed a thermometer directly into this ancient sea to check. Think of it like this: you have a detailed blueprint for a house, and you can see the finished exterior perfectly. The blueprint says the interior walls should be exactly 12.7 centimeters thick. You have never been inside to measure, but your entire understanding of architecture depends on that number being correct. A direct measurement of the neutrino background's temperature is that crucial interior measurement. Why is it so hard to take? The problem is that temperature for a particle is just a measure of its average energy or speed. These primordial neutrinos are now so cold they are almost stationary. Their energy is unimaginably tiny, millions of times weaker than even the neutrinos streaming from our sun. Designing a detector sensitive enough to not only notice these ghosts, but also to gauge their exact lethargy pushes our technology to its absolute limits. Any experiment must filter out the frantic buzz of modern neutrinos to sense the deep frozen drift of the ancient ones. A deviation, even a minuscule one, would send shockwaves through physics. If the temperature reads higher than predicted, it could mean we missed a source of extra energy in the early universe, perhaps from the decay of an unknown particle. If it reads lower, it might suggest neutrinos interacted with something else as they traveled, something like dark matter, sapping their energy over billions of years. That 1.95 Kelvin is more than a number, it is a seal of approval on our story of creation. Finding it exactly as predicted would be a triumph of human understanding. Finding it different would be an even greater discovery, a crack in the foundation revealing a hidden room we never knew existed. This precise temperature connects to a deeper, more profound puzzle. The universe we see is made almost entirely of matter, from the stars to our own bodies. But our best theories say the Big Bang should have created equal amounts of matter and antimatter, a perfect symmetry that would have annihilated itself into pure energy, leaving behind a cosmos of light and nothing else. Something broke that symmetry, tipping the scales just 1 part in a billion in favor of matter. That tiny imbalance is the reason we exist. The third mystery asks if the ghostly neutrino sea was the architect of our material reality. The leading idea is called leptogenesis, a process where the heavy, early ancestors of today's neutrinos decayed in a lopsided way. In the unimaginable heat of the first fraction of a second, these particles would have produced slightly more matter neutrinos than antimatter antineutrinos. Through a complex cascade of interactions, that small excess in the neutrino sector could have been transferred or reprocessed into the excess of protons and electrons that built everything we see. The cosmic neutrino background is the cooled remnant of that entire population. If leptogenesis is true, then this fossil sea should carry an imprint of that original bias. It might not be a sea of perfectly equal neutrinos and antineutrinos, but one with a faint, frozen-in preference for matter. Detecting that preference, however, is a challenge of almost impossible subtlety. We are not looking for a dramatic difference, but for a 1 in a billion asymmetry frozen into particles that barely interact at all. How could we possibly measure it? The answer may lie in ultra-precise observations of how these ancient neutrinos subtly influence the large-scale structure of the universe. Their gravitational pull, though minuscule, helped shape how galaxies clumped together. A slight asymmetry in the neutrino background would have created a very specific, faint pattern in this cosmic web, a pattern next-generation telescopes might one day discern. Another possibility involves searching for a rare property called a neutrino's magnetic moment. If neutrinos act like tiny magnets, an asymmetric sea could leave a unique fingerprint on the polarization of the cosmic microwave background light. Finding any evidence would be revolutionary. It would mean the oldest particles in existence are not just silent witnesses to creation. They are the very reason creation resulted in something rather than nothing. Every atom in your hand owes its existence to a decision made in the first instant of time, a decision potentially recorded in the cold, dark sea flowing through you right now. But the story of matter's survival is tied to an even more fundamental property of these ghostly particles, a property the cosmic background could finally reveal. This is the fourth mystery, the puzzle of the neutrino mass hierarchy. To understand it, we must first accept a strange fact about neutrinos. They are not one, but three distinct types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And in a quantum quirk, a neutrino born as one flavor does not stay that way. It oscillates, constantly morphing between all three as it travels. This phenomenon proves they have mass, a discovery that shattered the old standard model of physics. But here is the catch: we know they have mass, but we do not know how much each one weighs, or more precisely, how their masses are ordered. Think of three siblings. You know they have different heights, but you have never seen them standing side by side. You cannot tell if the tallest is just slightly taller than the middle one, or if there is a dramatic gap. For neutrinos, there are two possible family portraits. The first is called the normal hierarchy. Here, the two lightest neutrinos are very close in mass, with the third being significantly heavier. The second is the inverted hierarchy, a complete flip where the two heaviest are close together and the third is the lightest. This is not just academic bookkeeping. The ordering dictates how neutrinos behave in extreme environments, like the cores of collapsing stars, and influences how they shaped the early universe. It is a key that unlocks deeper theories of particle physics. So how could the cosmic neutrino background, a fossil from a time before atoms, possibly tell us which hierarchy is correct? The answer lies in the fossil's fine print, its detailed energy spectrum. When the background was formed, the universe was so dense that neutrinos were constantly interacting, their flavors rapidly oscillating. The exact pattern of those oscillations in that primordial soup depended critically on the mass differences between the flavors. That pattern, that specific distribution of energies among the three types, got frozen into the background as the universe expanded and the neutrinos stopped interacting. It is like a photograph of a vibrating guitar string taken at the exact moment it was plucked. The blur in the photo reveals the string's fundamental frequency. In principle, if we could analyze the cosmic neutrino background with godlike precision, measuring the relative numbers of each flavor and their exact energies, we could read that frozen oscillation pattern. It would show us the original mass differences, revealing whether the family portrait is normal or inverted. No experiment on Earth can recreate the conditions of the first second, but that second left us its own recording. The implications stretch to the end of time. The mass hierarchy influences how neutrinos behave under their own gravity over cosmic eons. In an inverted hierarchy, the collective pull of these countless ghosts could subtly alter the fate of the universe's expansion on scales we cannot yet comprehend. The hierarchy is a small number with universe-spanning consequences, and it might be written in a script we have only just begun to decipher. The mass of a single neutrino is almost nothing, yet together they form a sea that may hold the blueprint for the universe's greatest shadow. This brings us to the fifth mystery, the potential conversation between the oldest particles and the most mysterious substance in the cosmos, dark matter. We know dark matter exists because its immense gravitational pull holds galaxies together and bends the path of light, yet it refuses to interact with light itself. It is the universe's silent partner, making up over 85% of all matter, and we have no idea what it is. The cosmic neutrino background might be the only witness to its true nature. Imagine dark matter as a vast, invisible crowd moving through a stadium. The ancient neutrinos are like a fine, cold mist filling that same space. If the crowd and the mist never touch, they pass through each other without a trace. But if even a few individuals in that dark crowd brush against the mist, they would leave a disturbance, a ripple in the neutrino sea. Certain theoretical models suggest this exact possibility. Some candidates for dark matter, like particles known as sterile neutrinos or weakly interacting massive particles, could occasionally scatter off the relic neutrinos. Over billions of years, even this faintest of interactions would leave a mark. It could subtly heat the neutrino background in specific regions or create faint anisotropies, patches where the sea is slightly warmer or more dense. Other theories propose that dark matter particles are unstable and decay over cosmic time, releasing energy that injects new, slightly more energetic neutrinos into the ancient background. This would be like adding a few warm droplets to our frozen sea, creating a specific distortion in its otherwise pristine energy spectrum. Detecting such an imprint would be a twofold revolution. First, it would prove that dark matter is not completely sterile, that it does interact with something besides gravity, even if that something is another ghost. Second, and more profoundly, it would turn the cosmic neutrino background into a brand new telescope. By meticulously mapping the temperature and density of this fossil sea across the sky, we could indirectly chart the distribution of dark matter throughout the universe's history. We could see where it clumped, how it flowed, and how its invisible architecture guided the formation of galaxies. The relic neutrinos would become luminous tracers, not with light, but with their subtle deviations from perfection. They would illuminate the dark universe by showing us where it has brushed against the oldest light of all. This means the key to understanding the dominant component of our reality might not be found by building bigger detectors for dark matter, but by learning to read the wrinkles in a sea of particles from the first second of time. The immense power of dark matter sculpted the cosmos, but it did not work alone. The sixth mystery reveals how the ghostly neutrino sea actively shaped the universe we see, acting as a cosmic sculptor with a light but decisive touch. To understand this, we must revisit the universe's infancy, a time before stars, when space was filled with a nearly smooth soup of dark matter and hydrogen gas. Gravity began to pull this material into denser clumps, the seeds of future galaxies. But streaming through this primordial soup were the neutrinos from the cosmic neutrino background, still incredibly energetic and moving at almost the speed of light in those early epochs. They were what cosmologists call a hot component. Think of trying to build a sandcastle on a beach with a strong wind constantly blowing. The wind doesn't stop the castle from forming, but it smooths out the finest details, erasing the smallest towers and intricate shapes. The streaming neutrinos acted like that cosmic wind. Their high speed and relentless motion meant they could not be trapped by the weak gravitational pulls of the very smallest clumps of matter. As they streamed out of these tiny potential wells, they carried energy away, effectively washing out the beginnings of small-scale structure. This suppression had a profound and lasting effect. It created a minimum size for the first clumps of matter that could successfully form. The universe's building blocks, therefore, started at a larger scale than they would have if neutrinos were massless and even faster, or if they did not exist at all. This imprint is not lost to time. It is fossilized in the present-day cosmic web. When we map the distribution of galaxies across billions of light years, we see a specific pattern, a characteristic spacing between the vast filaments and walls. That pattern reflects the initial suppression of small clumps. By analyzing this large-scale structure with powerful telescopes, cosmologists can read the subtle signature of the neutrino background's early influence. This provides one of the most powerful constraints we have on the total mass of all neutrino species combined. It works like a cosmic scale. Heavier neutrinos would have had more gravitational influence, but also would have slowed down sooner, changing the precise way they smoothed the early universe. The observed galaxy patterns tell us that the combined mass of the three neutrinos is incredibly small, certainly less than a millionth of the mass of a single electron. Yet, because there are so many of these particles outnumbering protons and electrons by over 1 billion to 1, their collective gravitational effect, sculpting the universe from its first moments, is undeniable. So the grand architecture of galaxy clusters and superclusters we see today is in part a monument to the lightest particles in existence. Their ghostly passage determined what could be built, setting the foundational blueprint for everything that followed. That sculpting power originated in a moment of unimaginable ferocity. The seventh mystery uses the cosmic neutrino background as a direct time machine to the universe's first picosecond, a realm no human experiment will ever touch. This is the electroweak epoch, when the universe was over a quadrillion degrees Kelvin and the fundamental forces of nature wore a single, unified face. The electromagnetic force, which governs light and chemistry, and the weak nuclear force responsible for radioactive decay, were not separate entities. They were one and the same, a single electroweak force. In that seething, primordial energy, particles like the W and Z bosons, which today are incredibly massive and short-lived, were as common and massless as photons. It was a reality governed by physics at energy scales so high they make the collisions inside our largest particle accelerator, the Large Hadron Collider, look like a gentle breeze. Then, as the universe expanded and cooled in that first second, a pivotal event occurred, the electroweak phase transition. This was the moment when the unified force split in two, giving us the separate electromagnetic and weak forces we know today. It was a cosmic symmetry-breaking event, akin to water freezing into ice, where the underlying rules of reality suddenly changed form, and it happened just before the neutrinos decoupled. This timing is everything. When the neutrino sea froze out of the hot particle soup 1 second after the bang, it captured a final, fleeting snapshot of that newly broken symmetry. The properties of the neutrinos, their abundance, their energy distribution, their very flavors were set by the precise conditions of the electroweak epoch. They are not just relics from the first second, they are relics from the moment the forces of nature themselves took their modern shape. So, by studying this fossil sea, we are indirectly probing energies 1,000,000 times more powerful than anything we can create. It is like trying to understand the inner workings of a star by analyzing a single, cold cinder that drifted to Earth. That cinder's atomic structure holds the history of the stellar furnace that forged it. In the same way, the precise statistical details of the cosmic neutrino background encode the physics of that ultra-high-energy realm. For instance, the exact ratio of neutrinos to photons in the background is a direct readout of the temperature and the number of particle species present during decoupling. Any deviation from the predicted number could signal the existence of unknown particles that were buzzing around in that early soup. Particles too heavy to be produced in any collider, but which left their fingerprint on the cooling universe. Furthermore, the way neutrinos interacted with the Higgs field, the field that gives particles mass, during the phase transition could have imprinted subtle asymmetries or distortions in their distribution. Detecting such a distortion would be like finding a fossilized ripple from the moment mass itself was born. This makes the ghostly background our only viable telescope for viewing the universe's most fundamental transformation. While particle physicists strain to push colliders to ever higher energies, cosmologists can look back to a time when the entire universe was such a collider. The data from that ultimate experiment is still flowing through us, frozen into a sea of silent messengers, waiting for us to learn their language. The frozen snapshot of the electroweak epoch may not be perfectly preserved. The eighth mystery asks a startling question: what if these ancient ghosts are slowly fading away? According to our best current model, the standard model of particle physics, neutrinos should be absolutely stable. Once created, they should drift through the cosmos forever, unchanged. But what if the model is incomplete? Several compelling theories beyond the standard model suggest that neutrinos could, in fact, decay, but over timescales so vast they make the age of the universe seem like a blink. This introduces a profound possibility. The cosmic neutrino background we are trying to detect might not be the original, pristine sea. It could be a faded remnant, a ghost of a ghost. How could a particle with such tiny mass even decay? The most common idea is that a heavier neutrino could transform into a lighter one by emitting something new, perhaps an ultralight, never-before-seen particle often called a majoron, or even a photon of incredibly low energy. This process would be unimaginably slow, but over 13.8 billion years, even the rarest event could leave a mark on a population of countless trillions. So how would we see evidence of this invisible decay in the fossil sea? The signature would be in the energy spectrum. A stable cosmic neutrino background has a very specific, predictable distribution of energies, a perfect curve shaped by its hot birth and subsequent cosmic cooling. If a fraction of the original neutrinos have decayed, that curve would be distorted. The highest energy relics from the early universe would be slightly depleted, as they are the most likely to have transformed. It would be like examining a very old photograph and noticing that the brightest areas have faded more than the shadows, revealing not just the image but the passage of time itself. Our search for the background, then, becomes a double investigation. Detecting the sea at its predicted strength and energy would powerfully confirm neutrino stability. But finding it weaker than expected or missing its highest energy components could be an even more electrifying discovery. It would be direct evidence that neutrinos are not eternal, and it would point unequivocally to new physics, to particles or forces that have operated in perfect secrecy since the dawn of time. This decay would be a slow leak of information from our universe into something else entirely. Each decay event over an eon would be a whisper about realms and interactions we cannot yet conceive. The silent sea may be telling us that even ghosts do not last forever, and in their fading, they illuminate a cosmos far richer and more dynamic than our standard stories allow. The silent sea may not be perfectly still. While the cosmic microwave background is famously smooth, a near-perfect uniform glow, the ninth mystery asks if the neutrino background could be subtly lumpy. These are anisotropies, delicate ripples in the density of the ghost sea, and their existence would rewrite our understanding of how the lightest particles sculpt the cosmos. The leading theory suggests that over billions of years, the immense gravitational pull of cosmic structures like our own Milky Way galaxy and the even larger dark matter halos surrounding it could have begun to gather these ancient neutrinos. Think of a vast, invisible net slowly trawling through an ocean of mist, gathering a slightly thicker concentration of droplets in its threads. Because neutrinos have a tiny amount of mass, they must respond to gravity. The most sluggish, lowest energy neutrinos from the primordial sea would be the most susceptible, their paths gently curved by the pull of galaxy clusters and superclusters. Over cosmic time, this could create a faint pattern, a map where the neutrino sea is marginally denser in the directions of great mass concentrations and slightly thinner in the cosmic voids. Detecting this pattern is a monumental challenge. The variations would be exquisitely subtle, perhaps a change of just one part in a million across the sky. Our current technology is barely sensitive enough to hope for a direct detection of the background's uniform signal, let alone its minute ripples. Yet the pursuit is vital because these anisotropies are a direct test of gravity itself on the largest scales. They probe how Einstein's theory of general relativity applies to a fluid made of the most elusive particles, streaming across billions of light years. Finding the predicted pattern would confirm that neutrinos, despite their ghostly nature, obediently follow the cosmic gravitational landscape we have mapped with light. But a surprise would be even more revealing. If the anisotropies are stronger than expected, it could mean neutrinos interact with each other or with dark matter through a new, very weak force, enhancing their ability to clump. If they are weaker or absent, it might suggest our models of the large-scale gravitational field are incomplete, or that something prevented the neutrinos from clustering as expected. This lumpiness is a frozen record of a conversation between the universe's lightest particles and its heaviest structures. By learning to read its faint text, we would not just see the neutrino sea, we would see the gravitational imprint of the entire cosmic web upon it, a shadow of all creation cast upon its oldest relic. Gravity's pull on the neutrino sea hints at an even more extreme possibility from the dawn of time. The 10th mystery connects these ancient ghosts to the most enigmatic gravitational traps conceivable, primordial black holes. These are not the black holes formed from collapsing stars, but hypothetical monsters born in the first chaotic instants after the Big Bang, when the universe was a maelstrom of unimaginable density. In that seething cauldron, random fluctuations could have been so intense that pockets of space simply collapsed under their own weight, sowing black holes of all sizes directly into the fabric of the newborn cosmos. And the cosmic neutrino background was there, a dominant component of that early universe, potentially holding the key to their creation. One compelling theory suggests that these relic neutrinos themselves could have been the seeds. In regions where the neutrino sea was ever so slightly denser, its collective gravity, though feeble for individual particles, could have been enough to tip the balance. It would act as a gravitational anchor, pulling in the surrounding hot matter and radiation, concentrating it until it crossed the threshold of no return and birthed a black hole. In this scenario, the faint anisotropies, the lumpiness we just discussed, would not just be a later effect, but the very blueprints for a hidden population of ancient black holes. The implications spiral outward. If primordial black holes exist, they could solve several cosmic puzzles at once. They are a leading candidate for at least a portion of the universe's dark matter, these invisible gravitational anchors hiding in plain sight. They might even be the seeds for the supermassive black holes we find at the hearts of galaxies, objects so huge their origin is a mystery. But the conversation between the ghost sea and these gravitational pits is a two-way street. Primordial black holes are not necessarily eternal. According to Stephen Hawking's famous theory, black holes slowly evaporate, radiating away their mass over astronomical timescales. The smallest ones would evaporate the fastest, ending their lives in a final, energetic burst of particles. And what would be among those final emissions? Neutrinos, an evaporating primordial black hole would, in its last moments, inject a spray of new, energetic neutrinos into the surrounding space. This would create a subtle contamination of the pristine cosmic neutrino background. In regions of space where many small primordial black holes have died, the fossil sea would be slightly warmer, its perfect thermal spectrum tinged with these late-arriving particles. Furthermore, when two primordial black holes merge, they create ripples in spacetime called gravitational waves, but they also violently stir the surrounding medium. That medium in the early universe was the neutrino sea. A merging event could have sent powerful shockwaves through this relativistic fluid, creating unique, circular ripples of density in the background, frozen in place as the universe expanded. While these signals are fantastically faint, they represent a potential new window. We are learning to listen to the universe with gravitational wave observatories, and we are striving to detect the neutrino background. A correlation between the two, a specific gravitational wave signal paired with a hypothesized distortion in the relic neutrino map, would be the smoking gun. It would prove the existence of these primordial beasts and simultaneously use the oldest particles in existence as a witness to their violent dances. The silent sea may not just hold the seeds of black holes, but the echo of their collisions and the faint warmth of their final size. The possibility of ancient black holes evaporating into the neutrino sea touches on a deeper identity crisis for the particles themselves. This 11th mystery asks a question so fundamental it reaches to the quantum core of reality. Are neutrinos their own antiparticles? In the familiar world of electrons and protons, matter and antimatter are perfect opposites. An electron has a negative charge. Its antimatter twin, the positron, has a positive charge. When they meet, they annihilate in a flash of energy. But neutrinos are the odd ones out. They are electrically neutral, carrying no charge at all. This opens a profound and haunting possibility. What if a neutrino and its antimatter counterpart are not two different entities, but one and the same? A particle that is its own ghost. This special class is named after the physicist Eta Majorana. If neutrinos are Majorana particles, it would rewrite the rules of the quantum universe. The implications for the cosmic neutrino background are staggering. If neutrinos are their own antiparticles, then the sea from the Big Bang is not a mix of two distinct populations. It is a single, unified ocean of identical entities. The distinction between neutrino and antineutrino becomes meaningless, a label without a true difference. This changes the very chemistry of the early universe fossil, the processes that forged it, and the way it interacts with itself over cosmic time would follow a different set of quantum rules. How could this ancient sea possibly reveal such a subtle property? The answer lies in a delicate fingerprint imprinted during its creation. In the Majorana scenario, certain rare interactions in the hot early soup would have been possible, subtly altering the final energy spectrum and flavor composition of the frozen background in ways a Dirac or non-Majorana sea would not show. Detecting that specific distortion in the relic neutrinos is a dream for the distant future, but here on Earth, physicists are engaged in a monumental hunt for the same truth. They are searching for an extremely rare nuclear process called neutrinoless double beta decay. In a normal radioactive decay, a nucleus might spit out an electron and an antineutrino to achieve stability. In double beta decay, two electrons are emitted. According to standard physics, this must also release two antineutrinos. But if the neutrino is its own antiparticle, a miraculous cancellation can occur. The two antineutrinos could annihilate each other right at the moment of creation, vanishing into the quantum vacuum. The result, a decay that emits only two electrons with no neutrinos at all. Finding this event would be definitive proof that neutrinos are Majorana particles. Experiments deep underground, using ultra-pure crystals of germanium or xenon cooled to cryogenic temperatures, watch patiently for a tiny bump of energy at exactly the right value, a signature with no missing energy carried away by unseen neutrinos. It is a search for a needle in a cosmic haystack requiring decades of observation. This terrestrial quest and the cosmic fossil are intimately linked. They are probing the same fundamental physics from opposite ends of time. The neutrinoless double beta decay, if it exists, is a process that depends entirely on the Majorana nature of the neutrino. That same nature would have dictated how the cosmic neutrino background condensed out of the Big Bang. So, by studying the relic sea, we are, in essence, looking at the integrated history of every potential neutrinoless decay that could have ever occurred across the entire universe. A detection in a lab would confirm the theory. A precise measurement of the fossil sea could reveal its consequences on a cosmic scale. This mystery cuts to the heart of what these particles are. Are they unique quantum beings existing in a state of self-annihilation and creation, or are they merely another matched pair in the universe's matter-antimatter duality? The answer, hidden within the cold sea or a silent laboratory signal, would not just describe a particle, it would reveal a deeper symmetry or asymmetry woven into the fabric of space and time. The identity of a neutrino is written into the very atoms that make up our world. During the universe's first 3 minutes, the entire cosmos was a nuclear furnace of unimaginable scale, fusing the first atomic nuclei from a soup of protons and neutrons. This process, Big Bang nucleosynthesis, forged almost all the hydrogen and helium we see today, along with a trace of lithium. And the cosmic neutrino background was not a passive spectator, it was a director in this cosmic drama, its presence fundamentally altering the outcome. In those first searing minutes, the universe was so dense that neutrinos were still interacting frequently. Their energy and sheer numbers contributed significantly to the total energy density of the cosmos, which directly controls how fast the universe expands. A faster expansion means less time for nuclear reactions to occur before the soup becomes too thin and cool for fusion. The density of the neutrino sea, therefore, set the clock for creation itself. More neutrinos meant a faster early expansion, potentially shutting down the nuclear furnace too soon and leaving us with a different mix of primordial elements. But the influence was even more hands-on. Specific nuclear reactions that built helium were mediated by the weak force, the very domain of neutrinos. For instance, the crucial first step in forming helium is the conversion of a proton into a neutron. This process involves spitting out a positron and, critically, an electron neutrino. The rate at which this could happen, and the reverse process where a neutron turns back into a proton, was governed by a delicate dance with the sea of neutrinos and antineutrinos buzzing everywhere. The neutrino background acted like a constant background noise, either encouraging or suppressing these transformations, directly controlling the final ratio of protons to neutrons available for building heavier elements. This gives us a remarkable cosmic cross-check. The abundances of hydrogen, helium, and lithium that we measure in the oldest stars and pristine gas clouds are like a fossil record from those first 3 minutes. Our theories of Big Bang nucleosynthesis, which include precise calculations of the neutrino sea's influence, predict these abundances with stunning accuracy. The fact that the observed numbers match our predictions so perfectly is one of the strongest validations we have that our understanding of the early universe and the role of neutrinos within it is correct. It tells us the cosmic neutrino background was real, and it behaved exactly as our models say it did during that critical formative period. But this agreement is also a razor's edge. If future, more precise astronomical measurements were to find a tiny discrepancy in, say, the primordial lithium abundance, it could point directly back to the neutrino sea. It might suggest that the neutrino population was slightly hotter, denser, or had a different flavor mix than we assumed. The elements are the universe's original chemistry set, and the instructions for their creation were written by the ghostly particles flowing through them. So every star we see is not just a beacon of light, but a monument to a sea of neutrinos that guided its very first ingredients into being. The nuclear furnaces of the early universe forged the elements in a delicate dance with the neutrino sea, but this ancient relic might harbor a far stranger form of matter altogether. The 13th mystery plunges us into the quantum deep end, asking if the cosmic neutrino background could exist not as a simple gas of particles, but as an exotic quantum condensate or even a cosmic-scale superfluid. This is not science fiction, but a serious theoretical possibility arising from the unique properties of neutrinos. To understand it, we need to think about what happens when matter gets extremely cold and dense. In a lab, when you cool certain gases like helium to near absolute zero, something magical occurs. The individual atoms lose their distinct identities and merge into a single, coherent quantum state called a Bose-Einstein condensate. They stop behaving like separate balls in a jar and start acting like one giant, unified wave. This substance can flow without any friction at all, a property known as superfluidity. It can climb the walls of its container, form persistent currents that never slow down, and exhibit behaviors that defy our everyday intuition about liquids. Now apply that idea to the universe's oldest particles. The relic neutrino sea is certainly cold, at just under 2 degrees above absolute zero, but is it dense enough? Here is where the quantum nature of neutrinos becomes critical. If neutrinos are Majorana particles, as we discussed earlier, they belong to a class of quantum particles that can, under the right conditions, form such condensate. The immense number of neutrinos, outnumbering every other particle by billions to one, could provide the necessary density on a cosmic scale. the gravitational pull of the entire universe might act as the containing vessel holding this vast cold fluid together. If this happened, the implications would rewrite cosmology. A superfluid cosmic neutrino background would not behave like a simple collection of independent ghosts. It would act as a single, coherent quantum entity spanning the entire cosmos. Its influence on the large-scale structure of the universe would be profoundly different. Instead of just streaming freely and suppressing small clumps, a superfluid could exhibit collective behaviors like forming quantum vortices around galaxies or creating large-scale interference patterns that subtly guide the distribution of dark matter. Even more speculatively, some physicists have proposed that the peculiar properties of a cosmic neutrino superfluid could offer an explanation for dark energy, the mysterious force accelerating the expansion of the universe. In this model, the frictionless flow and internal pressure of the superfluid could generate a repulsive gravitational effect on the largest scales, gently pushing the cosmos apart. While this remains a highly speculative idea, it illustrates the transformative power of this concept. Detecting such a state, however, is a challenge of almost unimaginable subtlety. The signature would be in the fine details of how the neutrino sea interacts with gravity and with itself. It might leave a unique pattern in the gravitational lensing of distant galaxies or create specific, faint harmonics in the cosmic microwave background. The hunt is not for the particles themselves, but for the ghostly echo of their collective quantum behavior. This mystery pushes our understanding to the limit, forcing us to consider that the oldest substance in existence might be in a state of matter we have only ever created in tiny, controlled samples on Earth. It suggests the entire cosmos could be permeated by a frictionless quantum fluid, a silent supercurrent flowing through the voids, its unseen dynamics quietly shaping the fate of everything. The quantum sea of neutrinos may have orchestrated a force that sculpts galaxies from within. The 14th mystery asks if these ancient ghosts are responsible for weaving the universe's invisible magnetic tapestry. Across the cosmos, from the vast spaces between galaxy clusters to the hearts of stars, magnetic fields thread through the void. They are not mere decorations, they are fundamental actors, guiding cosmic rays, shaping the birth of stars, and influencing the structure of interstellar gas. Yet their origin is one of cosmology's great unsolved puzzles. How did these organized fields arise from a presumably neutral, featureless early universe? The answer might be written in the currents of the cosmic neutrino background. In the first seconds, the universe was not perfectly smooth. Tiny quantum ripples, the seeds of all future structure, were already present. Crucially, the sea of relic neutrinos may not have been perfectly uniform either. If there were slight asymmetries, more electron neutrinos flowing in one direction than antineutrinos in another, for instance, these would constitute a net electrical current. This is because neutrinos, while neutral themselves, interact through the weak force which is intimately linked with electromagnetism. A flowing current, even one made of neutral particles through subtle quantum effects, can generate a magnetic field. This process, known as a neutrino-driven dynamo in the primordial plasma, could have planted the faintest magnetic seeds across the entire infant cosmos. These seed fields would have been unimaginably weak, far weaker than the field of a common refrigerator magnet, but the universe had billions of years to amplify them. As gravity pulled matter into galaxies and clusters, it also stretched and wound these primordial magnetic lines like a cosmic spinner drawing out a thread. Turbulent motions within collapsing gas clouds, the rotation of galaxies, and the violent explosions of supernova all acted as natural dynamos, feeding on those initial seeds and strengthening them into the microgauss fields we detect today, weaving through spiral arms and galactic halos. The beauty of this idea is its direct testability. If the cosmic neutrino background truly planted these seeds, then the magnetic fields we see should bear a specific fundamental imprint. They should be present everywhere, even in the deepest, emptiest voids of intergalactic space, because the neutrino sea permeates everything. Their structure on the largest scales might reflect the original patterns of asymmetry in that sea. Current telescopes mapping faint radio emissions and the polarization of light from distant quasars are, in essence, tracing the outlines of this ancient magnetic architecture, searching for signatures that point back to a primordial origin. This connects the faintest particles to some of the most powerful engines in the cosmos. The same magnetic fields seeded by neutrinos go on to accelerate particles to nearly the speed of light, creating brilliant jets from black holes and painting the sky with synchrotron radiation. It means the ghostly background may have provided the initial spark for cosmic magnetism, a spark that galaxies then fanned into a universe-spanning flame, guiding the evolution of the very structures that would one day give rise to stars, planets, and us. These magnetic seeds grew within a cosmos governed by seemingly unbreakable rules. But what if the rules themselves are not quite as rigid as we believe? This 15th mystery uses the cosmic neutrino background as the ultimate laboratory to test the bedrock of reality, the principle of Lorentz invariance. This is the idea that the laws of physics are the same for all observers, regardless of how fast or in what direction they are moving. It is the cornerstone of Einstein's theory of relativity, the reason why light always travels at the same speed in a vacuum, and why your experience of time and space remains consistent. It is woven so deeply into our understanding that challenging it seems almost unthinkable. Yet, several ambitious theories of quantum gravity, attempts to unify the very large with the very small, suggest that at the most fundamental, microscopic level of spacetime, this perfect symmetry might fray. Think of spacetime not as a perfectly smooth, continuous sheet, but as a frothing quantum foam, a seething mesh of unimaginably tiny loops or grains. In such a turbulent environment, a particle's journey might not be perfectly smooth. Different energies or even different types of particles could experience this grainy structure in slightly different ways, leading to minuscule violations of Lorentz invariance over vast distances. This is where the ghostly sea becomes an instrument of unparalleled precision. The neutrinos of the cosmic neutrino background have been traveling for over 13 billion years, covering distances so immense they defy comprehension. If Lorentz invariance is violated, even by a factor of 1 part in a number with 30 zeros, the effects could accumulate over such an epic journey. It would be like detecting a single grain of sand shifted on a beach that stretches across a continent. For these ancient neutrinos, a violation could manifest in several subtle ways. Their speed might depend ever so slightly on their energy, meaning the highest energy relics in the background would arrive at our detectors with a timing difference compared to the lower energy ones, a difference that standard physics says should not exist. Alternatively, the way they oscillate between flavors over cosmic distances could be distorted, creating an unexpected pattern in the flavor composition of the fossil sea we hope to one day measure. By studying the detailed properties of this background, we are not just looking at particles, we are examining the integrity of spacetime itself across nearly its entire history. A detection of any deviation would be a seismic event in physics. It would provide the first experimental evidence for a theory of quantum gravity, pointing toward a deeper structure beneath the smooth continuum of relativity. It would mean that the universe has a preferred frame of reference after all, a fundamental grain to reality that becomes visible only on the scale of the cosmos itself. The silent, cold sea of neutrinos, therefore, is more than a fossil. It is the longest-running experiment in existence, a test of spacetime's symmetry that began at the dawn of creation and whose results are only now drifting within our reach. The very fabric of space through which we gaze is gently warped by an ocean of ghosts. This 16th mystery transforms the cosmic neutrino background from a passive relic into an active lens, a cosmic magnifying glass built from the cumulative gravity of the lightest things in existence. While a single neutrino's gravitational pull is vanishingly small, the sheer number of them is incomprehensible. Remember, they outnumber protons and electrons by over 1 billion to 1. This means that in any given volume of space, the total mass locked in this cold sea is significant, potentially rivaling the total mass of all the stars in the universe. And where there is mass, there is gravity, and gravity, as Einstein taught us, bends the path of light. This phenomenon, called gravitational lensing, is a powerful tool. We see it when massive galaxy clusters distort the images of galaxies behind them, stretching them into faint arcs and rings. The neutrino background does the exact same thing, but on a universe-wide scale and with an impossibly subtle touch. It is not a strong, dramatic lens like a galaxy cluster, but a weak, pervasive lens, a gentle, continuous warping of spacetime that affects every single photon traveling to us from the distant cosmos. This is neutrino lensing. Imagine looking at a distant cityscape through a perfectly clean, but ever so slightly wavy pane of glass. The buildings are not broken or wildly distorted, but their positions are minutely shifted, their shapes subtly sheared. The cosmic neutrino background is that wavy glass for the entire universe. As light from a far-off galaxy journeys for billions of years to reach our telescopes, it passes through this vast sea. The collective gravity of all those ancient neutrinos spread across the void imperceptibly tugs on the light's path, causing a tiny, systematic distortion in the galaxy's apparent shape and position. Detecting this effect is a monumental challenge in precision cosmology. The distortions are incredibly small, a fraction of a percent change in a galaxy's shape. To see it, astronomers must analyze the shapes of millions, even billions of galaxies, using sophisticated statistics to separate this universal neutrino sheer from the natural, random orientations of the galaxies themselves, and from the stronger lensing effects of visible matter and dark matter. This is the promise of next-generation sky surveys, like those planned with the Vera C, Rubin Observatory, and the Euclid Space Telescope. These projects will map the shapes and positions of billions of galaxies with unprecedented accuracy, creating the most detailed chart of cosmic shear ever made. Hidden within that immense dataset could be the unique fingerprint of the neutrino sea's gravity. By analyzing how the lensing distortion varies with distance, how it affects galaxies 10 billion light-years away versus those only 5 billion, cosmologists can essentially perform a tomography of the universe's mass distribution. They can peel back layers of time, and one component of that mass, smooth and spread evenly throughout, would be the cosmic neutrino background. Mapping its distribution through lensing would be a revolutionary achievement. It would allow us to see this ghostly sea not by catching the particles themselves, but by observing their collective shadow on the rest of creation. It would provide a direct measure of the total mass of all neutrinos, confirming the constraints from large-scale structure in an entirely independent way. More thrillingly, it could reveal if the sea is perfectly smooth, or if it contains the faint ripples and lumps we discussed earlier, the anisotropies caused by the gravitational pull of galaxies. This would turn the entire sky into a neutrino detector, using the light of distant galaxies as our probe. So the next time you see a breathtaking deep-field image from the James Webb Space Telescope, filled with thousands of twisted ancient galaxies, remember you are not just looking at light. You are looking at light that has been on an epic journey, subtly guided and bent by the silent, persistent gravity of the universe's oldest particles. Their faint touch is written into the very shapes of everything we see. That pervasive lensing effect is a whisper of gravity from a silent sea, but the cosmos also screams. The 17th mystery listens for the echoes of cosmic violence within the neutrino background itself. When the universe tears itself apart in events of staggering power, a supernova's final detonation, the cataclysmic merger of two neutron stars, or the jet from a ravenous black hole, it does not just blast light and gravitational waves into the void. These cosmic cataclysms are also prodigious factories for neutrinos, producing torrents of high-energy particles that race outward at nearly the speed of light. For a brief, brilliant moment, a single point in space becomes a blazing beacon in the neutrino sky, and that beacon shines directly into the cold, dark sea of relic neutrinos surrounding it. This creates a fascinating possibility, a temporary distortion in the local cosmic neutrino background, a kind of neutrino echo. Think of the relic sea as a vast, still pond, frozen and perfectly calm for billions of years. Now drop a massive stone into its center. The impact sends out powerful ripples that disturb the entire surface. In our cosmic analogy, the stone is the supernova or merger, and the ripples are the burst of new, energetic neutrinos. But here is where it gets truly interesting. The pond is not made of water, it is made of other, much slower particles. The high-energy burst from the cataclysm does not just travel through the relic sea, it can interact with it. Through rare weak force collisions or even more subtle quantum effects, the incoming torrent can momentarily energize, scatter, or otherwise perturb the local population of ancient cold neutrinos. It is as if the stone's impact not only created waves, but also briefly warmed a patch of the frozen pond, changing its very nature. This perturbation would be a fleeting signal, a tiny, localized warping of the background's perfect thermal equilibrium. After the initial flash of the cataclysm fades, this disturbed patch of neutrino sea would slowly relax back to its cold, uniform state, but not instantly. For a short period, perhaps minutes, hours, or even days, that region of space would hold a memory of the violence in the form of a slight excess of neutrinos with a slightly different energy spectrum. Detecting such an echo is a challenge that pushes the boundaries of futuristic instrumentation. It would require a neutrino observatory capable of not only detecting the initial flash from a cosmic cataclysm, but also of monitoring that precise patch of sky with incredible sensitivity in the aftermath, searching for a faint, lingering hum that differs from the expected background noise. It would be like trying to hear the reverberation in a cathedral long after the bell has stopped ringing while standing in the middle of a roaring city. The scientific payoff, however, would be transformative. Catching a neutrino echo would give us a completely new way to study these extreme events. The echo's duration and properties would encode information about the cataclysm itself, such as the total energy released in neutrinos and the geometry of the explosion. Even more profoundly, it would provide a direct laboratory to study how neutrinos interact with each other over astronomical distances. The strength of the echo would depend on the probability that a high-energy neutrino from the burst scatters off a relic neutrino, a process so rare it has never been observed. Measuring it would tell us fundamental things about neutrino cross-sections and behavior in ways no particle collider ever could. Furthermore, by observing echoes from cataclysms at different distances, we could use the cosmic neutrino background as a fixed medium to probe the expansion history of the universe. The echo's properties would change depending on how much the relic sea has been stretched and cooled by cosmic expansion since the burst occurred. This turns the ghostly sea into both a canvas and a tool, recording the shockwaves of the universe's most violent moments and offering us a novel way to measure the cosmos itself. So the next time telescopes announce a neutron star merger in a distant galaxy, know that alongside the flash of gamma rays and the ripple of gravitational waves, there may be a quieter, slower signal fading in the dark, a whisper from the oldest sea as it is briefly stirred by the death throes of stars. The violent echoes of stellar cataclysms travel through a cosmos that is, for neutrinos, almost perfectly clear. This leads us to the 18th mystery, a beautiful paradox of transparency and fog. While the universe is overwhelmingly transparent to these ghostly particles, allowing them to cross billions of light years without a single interaction, the cosmic neutrino background itself creates the faintest possible mist. This relic sea presents a tiny but real scattering probability for the most energetic neutrinos in the cosmos. To understand this, picture two different kinds of travelers. The first are the ancient cold neutrinos of the background, drifting slowly and filling all of space like a deep, still fog. The second are the ultra-high-energy neutrinos, the cosmic bullets fired from the most powerful engines in the universe, like active galactic nuclei or tidal disruption events. These particles scream across the cosmos at energies millions of times greater than those produced in our largest particle accelerators. When one of these high-speed bullets encounters one of the nearly stationary fog particles, a remarkable and rare event can occur. They can actually collide. It is not a collision in the traditional sense of two billiard balls hitting, but a subtle interaction mediated by the weak nuclear force, the same force behind radioactive decay. The probability is vanishingly small, but the distances involved are incomprehensibly vast. An ultra-high-energy neutrino traveling from the edge of the observable universe will pass through an ocean of relic neutrinos so immense that even a 1 in a quintillion chance adds up. Over its epic journey, it might experience a handful of these weak scatterings. Each scattering would rob the high-energy neutrino of a little bit of its energy and deflect it slightly off its original course. From our perspective, this creates a subtle absorption effect. If we point our neutrino telescopes at a known, distant source of these cosmic bullets, we would expect to see a specific spectrum of energies arriving. But if the cosmic neutrino background is truly there, acting as a faint fog, the very highest energy neutrinos from the most distant sources would be slightly depleted. They would have been more likely to scatter and lose energy or be deflected away during their long journey. It is like looking at a brilliant lighthouse through a very thin haze. The brightest part of its beam is softened ever so slightly. Detecting this absorption dip in the energy spectrum of astrophysical neutrinos would be an indirect but powerful confirmation of the relic sea's existence and density. It would not require us to catch the cold neutrinos themselves, but to observe the shadow they cast on their more energetic cousins. Experiments like the Ice Cube Neutrino Observatory at the South Pole, which detects the faint flashes of light produced when high-energy neutrinos interact with the Antarctic ice, are already mapping the astrophysical neutrino sky. As their catalogs grow and their measurements of neutrino energies become more precise, they might one day see this predicted attenuation. It would appear as a faint deficit, a gentle dimming of the signal at the highest energies from sources at the greatest distances. Finding it would be a triumph of cosmic deduction. It would mean we have used the universe's most elusive particles to detect the universe's oldest particles, using one ghost to illuminate another. This faint fog, this sea of ancient relics, is not just a passive fossil. It is an active component of the cosmos, a medium that subtly filters the most extreme messages the universe sends our way. The faint fog of ancient neutrinos may be obscuring our view of the cosmos's ultimate speedometer. This 19th mystery ties the ghostly sea directly to one of modern cosmology's most urgent and puzzling crises, the Hubble tension. At its heart, it is a simple but profound disagreement about a single number, the Hubble constant, which tells us how fast the universe is expanding today. We have two primary, incredibly precise ways to measure it. The first method looks locally, using pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies to build a cosmic distance ladder, step by step, to gauge the current expansion rate. The second method looks back to the infant universe, using the detailed snapshot of the cosmic microwave background from when the universe was only 380,000 years old, and then running our cosmological models forward in time to predict what the expansion rate should be today. These two methods, one a direct measurement of the present and the other a pristine record of the past, should agree. They do not. the local measurements consistently give a faster, more frantic expansion rate than the prediction from the early universe. This is not a small discrepancy. It is a stubborn, statistically significant tension that has persisted for years, defying reanalysis and improved data. It suggests one of two unsettling possibilities. Either there is a hidden, systematic error in one of our measurement techniques that we have not yet uncovered, or our standard model of cosmology is missing a crucial ingredient. This is where the cosmic neutrino background enters the stage as a potential peacemaker or a provocateur. The properties of neutrinos are woven directly into the equations that connect the early universe to the present day. Specifically, two neutrino-related factors are critical: their total mass and their behavior as a form of radiation in the early cosmos. First, consider their mass. The combined gravity of all the neutrinos in the relic sea subtly slows the growth of cosmic structure over time. A higher total neutrino mass means more gravitational braking, which changes how galaxies cluster. This, in turn, affects the calibration of our distance ladder and the interpretation of the cosmic microwave background data. If the true total mass of neutrinos is different than the value currently assumed in our models, it could shift the predicted present-day expansion rate from the early universe measurement, potentially bringing it into alignment with the local observations. Second, consider their early role. In the first few 100,000 years, neutrinos were a major component of the universe's radiation content, zipping around at near light speed and influencing how quickly the primordial plasma could clump under gravity. The precise details of this neutrino-driven suppression of small-scale structure are encoded in the cosmic microwave background patterns. If the relic sea had properties we do not yet understand, perhaps due to an exotic interaction or a different temperature, it would alter those patterns and change the derived expansion rate. The ghostly background, therefore, sits at the crossroads of this crisis. A precise, direct detection and characterization of the cosmic neutrino background would give us an independent, firm measurement of neutrino properties that are currently only inferred indirectly. It would remove a major source of uncertainty from our cosmological models. If, after pinning down the neutrino sea, the Hubble tension remains, the case for new physics becomes overwhelming. It would point to something truly missing from our cosmic recipe, perhaps a new type of dark energy that evolved over time, or a modification to gravity itself on the largest scales. But if the tension resolves once we correctly account for the neutrino sea's true nature, it would be a monumental validation of our entire cosmological framework. The silent sea holds the key to determining whether we are misreading the cosmos's most fundamental metric, or if the universe is subtly more complex and wondrous than our best theories have yet dared to dream. The expansion rate of the universe is written in the cosmic ledger, a ledger that may be far more detailed than we ever realized. The 20th mystery asks if the ghostly neutrino sea is not just a fossil, but the universe's original memory chip, a cosmic hard drive encoding the deepest secrets of quantum reality. This ventures into the most speculative and profound ideas at the intersection of cosmology and quantum information theory. It begins with a notorious puzzle known as the black hole information paradox. According to quantum mechanics, information, the specific identity and state of every particle that falls into a black hole, can never be truly destroyed. Yet, according to classical general relativity, a black hole evaporates via Hawking radiation, which appears to be purely thermal, random noise containing no information about what fell in. This creates a paradox. Does the information vanish, violating quantum law, or is it somehow preserved? The leading resolution involves the holographic principle, the mind-bending idea that all the information describing a three-dimensional volume of space can be encoded on a two-dimensional surface surrounding it, like a cosmic hologram. The event horizon of a black hole is thought to be such a surface, with every bit of infalling matter leaving a scrambled imprint on it, which is then slowly radiated back out in the Hawking glow. Now stretch this concept to the ultimate scale. What if the entire observable universe in its first fiery instant also behaved according to holographic principles? The boundary of our observable cosmos is not a physical wall, but a limit in time, the surface of last scattering from which the cosmic microwave background comes. Could there be an even more fundamental surface, a horizon from the first moment where the information of creation was imprinted? This is where the cosmic neutrino background enters as a potential player. It is the oldest particle background, decoupling even before the microwave background. In those first instants, the universe was an unimaginably dense, hot soup where quantum gravity reigned. Processes we cannot yet describe, the possible birth and evaporation of primordial black holes, the violent fluctuations of spacetime foam, the very act of the universe emerging from a singularity would have generated immense amounts of quantum information. If that information had to go somewhere, to be preserved in some form to satisfy cosmic quantum law, the earliest and most pervasive medium to condense out of that chaos was the neutrino sea. Think of it like this: when a stone is dropped into a pond, the ripples carry information about the stone's size, shape, and impact. The Big Bang was the ultimate stone, and the first particles to freeze out of the resulting turbulence were these neutrinos. Their specific configuration, the exact patterns of flavor, energy, and momentum across the sky might not be random thermal noise. It could be a scrambled, holographic imprint of the universe's initial quantum state, a faint but permanent record of everything that happened in that first incomprehensible fraction of a second. They would be the universe's first and most fundamental pixels. Detecting this is, of course, a challenge of almost mythical proportion. It would require not just detecting the background, but mapping its properties with godlike precision, searching for subtle, non-random correlations and patterns in its distribution that no standard thermal process could create. It would be like looking at static on an old television screen and discovering, upon impossibly close inspection, that the snow contains a perfectly encoded digital copy of the first film ever made. The implications would be nothing short of ontological. It would suggest that the universe inherently remembers its own birth in the fabric of its oldest particles. The cosmic neutrino background would become more than a relic. It would be a literal cosmic archive. We could, in principle, decode it to learn about the conditions of quantum gravity, to understand what, if anything, came before the Big Bang, or to verify theories of how spacetime itself crystallized from a more fundamental order. This transforms the sea from a passive fossil into an active library, its silent particles each holding a minuscule piece of the ultimate code. While this remains a breathtaking speculation far beyond our current experimental reach, it reframes the entire quest. We are not just hunting for ancient particles, we are attempting to read the first chapter of a book written in a language of ghosts, a chapter that might contain the entire story of reality. The universe's original memory chip is a whisper we are only now learning how to hear. This 21st mystery confronts the staggering technological frontier standing between us and the cosmic neutrino background. We know the sea is there, bathing the earth in a ceaseless, ancient tide, yet building an ear sensitive enough to detect its faint hum is arguably the greatest engineering challenge in all of science. The proposed PTOLEMY experiment, aiming to catch these cold neutrinos with tritium, is just the beginning of a quest that will push material science, quantum mechanics, and sheer human ingenuity to their absolute limits. Beyond it lies a landscape of even more futuristic concepts, each a testament to our determination to commune with the dawn of time. One promising avenue exploits a quantum phenomenon known as coherent neutrino scattering. When a neutrino's wavelength becomes large enough, a property of its incredibly low energy, it can interact with an entire atomic nucleus at once, rather than with a single quark inside it. This coherent effect amplifies the tiny chance of interaction, but only just barely. To exploit it, physicists envision detectors made of ultra-pure, supercooled crystals, kept at temperatures within 1,000th of a degree above absolute zero. In such a frigid, pristine environment, the minuscule heat deposit from a coherent neutrino scatter could, in theory, be measured as a tiny, precise rise in temperature. It is like trying to feel the warmth of a single snowflake landing on a glacier while standing in a blizzard. The entire apparatus must be shielded from cosmic rays deep underground, isolated from vibrations and protected from the faintest background radioactivity. Every component, from the wiring to the structural supports, must be made from materials meticulously selected for their radio purity. Even the natural decay of atoms in the detector's own walls could drown out the signal. Another frontier involves quantum sensors that operate at the very edge of the Heisenberg uncertainty principle. Devices like superconducting quantum interference devices, or SQUIDs, and emerging quantum microcalorimeters can detect changes in magnetic fields or energy deposits with almost supernatural sensitivity. Coupled with advanced AI to sift through petabytes of data for the statistical signature of the background, these sensors form the nervous system of the next-generation hunt. Perhaps the most speculative idea of all is to detect the sea not through the weak force but through gravity itself. Each passing neutrino exerts an unimaginably small gravitational tug. While one neutrino's pull is irrelevant, the collective pull of the sea is a constant, smooth force. In principle, an exquisitely sensitive gravitational wave detector of the far future, perhaps one based on measuring the quantum states of levitated particles in vacuum, might one day sense the gentle pressure of this ghostly tide washing over it. This would be the ultimate non-interaction, detecting the sea by feeling its weight rather than its touch. The common thread is a fight against noise at a fundamental level. The signal has been here for Earth's entire existence, a 4.5 billion-year-old broadcast. Our challenge is not to receive it, but to build a radio quiet enough to hear it over the roar of the modern universe. It requires inventing new forms of silence. Success would be a triumph that echoes beyond astrophysics, driving advances in quantum computing, materials science, and precision measurement that will ripple through technology for generations. The quest to capture the cosmic neutrino background is not just about looking back. It is about forging the tools that will define our future perception of reality. That quest for silence forces a profound shift in perspective. The 22nd mystery is not about physics, but about philosophy, about what it means to live immersed in a living fossil of creation. To detect the cosmic neutrino background is to reach across 13.8 billion years and touch the universe in its first second of existence. It transforms our understanding of empty space. That void between stars, the apparent nothingness surrounding our planet, is not empty at all. It is a museum, and every single cubic centimeter of it is a display case holding a sample of the most ancient substance known. The air in your room, the space inside your lungs, is filled with these relics. You are not just in the universe, you are of it, in the most literal and intimate way possible, built from stardust and constantly washed by the primordial tide. This invisible sea connects all points in space and time. The neutrino passing through you now is the same, in essence, as the one that witnessed the formation of the first hydrogen atom, that felt the gravity of the earliest dark matter clumps that streamed through the core of a dying star 1 billion years before our sun ignited. It is a thread stitching together every event in cosmic history. To finally see this background would be to complete a sensory picture of reality we have only inferred. For all of human history, we have interpreted the cosmos through light, from campfires to telescopes. Light shows us the universe's face, its brilliant surfaces and energetic youth. But light is a latecomer, trapped for hundreds of thousands of years in the hot plasma of the early cosmos. The neutrino sea is the universe's hidden foundation, the underlying structure that was laid down first. Detecting it is like hearing the deep, foundational note of a cosmic chord, a note that has been resonating since before there was sound. It grounds our grand cosmological theories in tangible, physical reality. The Big Bang transitions from a powerful mathematical model to a concrete event we can sample directly, like a geologist holding a 4-billion-year-old zircon crystal. This changes our place in the narrative. We are not just distant observers looking out at a separate cosmos. We are embedded within an artifact of its origin, participants in a story that began long before life or planets or even atoms existed. The silent sea makes the entire universe a sacred site, and our growing ability to perceive it marks a milestone in consciousness. We are the universe beginning to understand its own birth, listening for the echo of its first breath in a sea of ancient ghosts. That deep connection to the Big Bang's first second makes this ghostly sea the ultimate referee. Our 23rd mystery places the cosmic neutrino background at the center of a cosmic courtroom, where it acts as the final judge for every theory that dares to challenge the standard story of creation. For decades, the Big Bang model has reigned supreme, supported by pillars of evidence like the expanding universe and the cosmic microwave background. Yet, brilliant minds have proposed compelling alternatives, visions of a cosmos that cycles through endless births and deaths, or one where the very laws of physics were different at the beginning. Each of these theories makes a specific, testable prediction about what should be in that fossil sea. The moment we finally measure it, we will hold the evidence to potentially rule them all out. Consider the idea of a cyclic universe, one where a Big Bang is not a singular beginning, but merely the latest turn in an endless loop of expansion, contraction, and rebirth. In such a model, each cycle would not start from a perfect singularity of infinite heat and density. There would be a prior history, a residue from the universe that came before. That residue would inevitably leave an imprint on any relic background formed in the new cycle. The cosmic neutrino background we detect, therefore, would not be perfectly thermal and smooth as the standard model predicts. It might carry a faint memory, a statistical whisper of structure, or a specific distortion in its energy spectrum, a fossil within a fossil from a prior cosmic epoch. A perfectly pristine, thermal sea would be a powerful argument against an endless cyclic history. Similarly, bouncing cosmologies where our universe emerged from the collapse of a previous one face a stringent test. The bounce itself is an event of unimaginable violence, likely involving quantum gravity effects that could inject tremendous energy. This would superheat the particle soup at the dawn of our cycle. The neutrinos that decoupled in that aftermath would bear the scars. Their background might be much hotter than our calculated 1.95 Kelvin, or it might contain a non-thermal tail of extremely high energy particles like splatters from the cosmic collision that birthed us. A detection that matches the cold, serene predictions of the standard Big Bang would cast severe doubt on these dramatic bouncing scenarios. Even more radical are models that suggest the fundamental constants of nature, like the strength of gravity or the weak force, were not always constant. They could have varied slowly over cosmic time. This is not a small adjustment. It changes the entire recipe of the early universe. The rate at which neutrinos decoupled from the primordial soup, their abundance relative to photons, even their effective temperature, all depend exquisitely on the values of these constants. If the weak force was stronger in the past, neutrinos would have stayed coupled to matter longer, freezing out later and at a different temperature. The resulting cosmic neutrino background would be measurably different in density and energy. A precise measurement of the sea's properties is therefore a direct measurement of the laws of physics as they stood in the first second. If it matches predictions based on today's constants, it powerfully affirms that the rules have been stable for almost 14 billion years. A mismatch would be a revolution, suggesting the very fabric of reality is malleable. This turns the search for the ghostly background into a process of elimination on a grand scale. We are not just looking for a relic, we are conducting an experiment that began at the dawn of time. an experiment whose results can invalidate entire libraries of theoretical work. The Silent Sea holds the only direct evidence from that inaccessible epoch. Philosophers and physicists can imagine 1,000 different origins for the cosmos, but the universe only had one. The neutrinos that have traveled since that moment are the sole surviving witnesses to what actually occurred. Their testimony, once we fully hear it, will settle arguments we have been having for generations. It will either coronate our standard model as a true description of reality's birth, or it will hand the keys to the cosmos to a new, more wondrous theory we have yet to fully conceive. The ultimate testimony of the cosmic sea forces us to confront a staggering coincidence. Our 24th mystery asks why this particular neutrino background, with its specific, delicate properties, exists in the universe that produced us. This is the realm of the anthropic principle, the observation that the universe we observe must be compatible with the existence of observers. And when we apply this to the cosmic neutrino background, the fine-tuning becomes breathtakingly clear. The mass and density of these relic neutrinos are not arbitrary numbers. They are critical dials on the cosmic control panel, and they are set to a very narrow range that allows for galaxies, stars, planets, and life. Consider a simple change. What if neutrinos were just a little bit heavier? We know their combined mass is incredibly small, but even a tiny increase would have had catastrophic consequences. Heavier neutrinos would have slowed down much earlier in the universe's history. Instead of streaming freely and suppressing only the smallest clumps of matter, they would have acted like a heavier, more sluggish fluid. Their collective gravity would have been stronger, pulling more fiercely on the primordial hydrogen soup. This might sound like it would help structure form, but the opposite is true. Their early sluggishness would have caused them to collapse into enormous, diffuse clouds under their own gravity, dragging ordinary matter with them. This would have smeared out the delicate density ripples that were the seeds of galaxies. The result would be a universe devoid of the fine cosmic web we see, a place where matter is spread in bland, featureless pools with no dense knots to ignite as stars. No stars means no planets, no heavy elements, and certainly no life. Now imagine the other side of the coin. What if the neutrino sea were vastly more dense, with 10 or 100 times more particles? Remember, in the early universe, these particles were a form of radiation, zipping around at near light speed. A denser sea would have dominated the expansion rate for a longer period, causing the universe to expand faster in its youth. This would have given gravity even less time to pull matter together before it was diluted into nothingness. The cosmic construction project would have been shut down before it even began. The first proto-galaxies would never have coalesced, leaving the cosmos a dark, empty, and forever simple place. The fact that we are here to ponder this means our universe does not have such a stifling neutrino fog. The sea is sparse enough to let gravity work its slow, patient magic. This fine-tuning extends to the neutrino's most famous feature, its ghostly ability to pass through matter. If neutrinos interacted even slightly more strongly with ordinary matter, they would have played a far more disruptive role in the cores of the first stars. They would have carried energy away too efficiently, cooling the stellar interiors and altering the nuclear fusion processes that forge carbon and oxygen, the very elements essential for life. A universe with more sociable neutrinos might be a universe without the chemistry of biology. So, what are we to make of this? The cosmic neutrino background we have, with its precise, minuscule mass and its specific, vast density, appears to be perfectly calibrated. It is a background that suppresses just enough small-scale structure to create an orderly cosmic web, but not so much that it prevents galaxy formation. It contributed to the expansion history in a way that allowed for both rapid early growth and the later emergence of complexity. This leads to a profound and, for some, unsettling question. Is this perfect calibration a lucky accident in a single universe, or is it evidence that our cosmos is just one of many in a vast multiverse? In a multiverse, countless universes bubble into existence, each with different fundamental constants and particle properties. In most of them, the neutrino background would be too heavy, too dense, or too interactive, rendering them sterile and dark. We, of course, find ourselves in one of the rare, finely tuned exceptions where the ghostly sea is just right, allowing for observers to arise and wonder at its existence. This does not provide a scientific explanation, but it frames our discovery in a new light. Detecting and measuring the cosmic neutrino background is not just about uncovering the past, it is about taking the precise measurement of a cosmic boundary condition for life itself. We are not just mapping a fossil, we are reading the user manual for a habitable cosmos, written in the language of its oldest particles. The silent sea, therefore, holds the answer to why we are here to search for it, a closed loop of observation that ties our existence directly to the first second of time. That fine-tuning for life points toward a final, unifying truth about this ancient sea. The 25th mystery reveals the cosmic neutrino background as far more than a fossil. It is the universe's fundamental currency. Just as a single currency can be used to trade for food, materials, and labor, this ghostly sea is the medium of exchange that connects every major domain of physics. It is the universal translator between the quantum realm and the cosmic stage, the ledger where the accounts of the universe are kept. Particle physics, cosmology, astrophysics, and gravity are not separate kingdoms. They are interconnected markets, and the neutrino background is the coin that circulates through them all. Consider a single transaction. In particle physics, we ask about the neutrino's mass and whether it is its own antiparticle. That fundamental identity, imprinted in the sea, dictates how it interacts with the Higgs field, a transaction recorded in the early universe's energy budget. This budget then flows directly into cosmology, governing the expansion rate and the growth of structure, determining the shape of the cosmic web we observe today. That large-scale structure, in turn, becomes the domain of astrophysics, where galaxies form and stars explode, events that themselves produce new neutrinos that momentarily distort the ancient background. And underpinning every step of this chain is gravity. The force that pulls on the sea is shaped by it and uses it as a lens to bend the light from distant galaxies. Each mystery we have explored is not an isolated puzzle. It is a single thread in a grand, interconnected tapestry. The question of the sea's temperature is linked to the Hubble tension. The search for its anisotropies is tied to the nature of dark matter. The possibility of it being a superfluid whispers about quantum gravity. Solving any one of these mysteries in isolation would be a monumental achievement, but solving them together, by finally measuring and understanding this background, would provide something far greater, a complete and consistent picture of the universe. It would be a narrative that flows seamlessly from the quantum fluctuations of the first picosecond to the majestic spiral of a galaxy like our own, all accounted for in the properties of a single, pervasive substance. This is the ultimate promise of the ghostly sea. It offers a unified receipt for the cosmos, a single statement that itemizes everything from the birth of forces to the arrangement of galaxies. To decode it is to hold a theory of everything not as an abstract equation, but as a physical, measurable reality that has been flowing through us since the beginning. The silent sea is the universe's own bookkeeping, and we are on the verge of learning how to read the ledger. This ghostly sea of ancient neutrinos is the universe's final, most eloquent witness. We have journeyed through 25 profound mysteries, from the quest to hear its faint whisper to its role as cosmic sculptor, from its potential identity as a quantum superfluid to its testimony in the court of cosmology. Each mystery reveals that the cosmic neutrino background is far more than a scientific curiosity. It is a cornerstone of reality, the fundamental currency connecting the quantum realm to the cosmic stage, the Big Bang's first second to the galaxies we see today. Unlocking these secrets demands a breathtaking fusion, A marriage of colossal imagination to envision a cosmos written in ghosts, and microscopic precision to build instruments delicate enough to hear them. It is a quest that defines our species, reaching across 13.8 billion years to touch the very beginning. So stay curious. The next great cosmic discovery might not blaze in the light of a distant star, but hide in the faintest whisper of the Big Bang, a whisper flowing through you at this very moment. We would love to hear which of these 25 mysteries captures your imagination the most. Share your thoughts in the comments below.